Hi everyone. Thanks for coming out tonight. You guys are awesome for being here. My name is Minh. I currently work at the Ontario Institute for Cancer Research, or OICR for short. I'm a software developer by day. By night, I organize and mentor at a meetup group called GraphQL Toronto, where we're a group of just Aspire developers getting together, learning to code, sharing experiences, whatnot. If you guys are interested, we meet every Saturday at Lighthouse Lab. Anyway, so it's not so often you get to work at a completely open source nonprofit organization where you feel great about what you do. So when I was approached about giving a talk about GraphQL, I thought it was a good fit to sort of introduce what we do at the OICR and how we're using GraphQL to fight cancer. Really, when I first joined the OICR about a year ago, hearing all these terms like genomics, data portal, ETL, I was like, what? And I was that kid. I was like, all right, I'm just going to pretend to understand what all these people are talking about, but really I have no idea. So really, to understand what we built at the OICR, I kind of need to know a little bit about this domain. Long story short, genomics is, in cancer research, the goal is to study the human genome and spot patterns that cause cancer, essentially. And so, as you guys might know, the human DNA is made up of a bunch of sequence of A, T, C, and G. So, different patterns of A, T, C, G creates different cells and basically creates the variation between different people. And so to study the human DNA, we essentially need to collect the samples, read the patterns in a process we call DNA sequencing, and then spot the difference in patterns. And so this DNA sequencing process is something that was historically very expensive and was a big endeavor for the humankind. And so back in 2001, and I completely just found this off Google, but the cost of sequencing a single human genome was like, I don't even know how to read that, $100 million. That's a lot of zeros. And notice that it's a logarithmic scale, so by 2015 the cost has gone down to close to 1,000, and now we have companies like 23andMe that does it for less than $1,000 for OU. So the byproduct of this is that we get a lot of data. So now the challenge is, how do we make this data accessible to researchers in the community? So that's where the work that we do at the OICR comes in. We build a lot of these things called data portals. Basically, through data portals, we provide the infrastructure to store all of these genomic data files, search through them, download reports and files, and work with the portal in the cloud. Work with the data in the cloud. And really the most complex part of this is actually searching through this. Of course, there are other complex parts of it as well, but we built different and integrate with third-party services to handle all of that. So really, what we built is glorified faceted search page. And these are a few of the portals that we've built so far at the OICR, and a couple more. ICGC was the first, followed by GDC, and then the most recently released, actually just last week, was the Kids First portal, and more of them. And you might have noticed by the look of these three, they pretty much all look the same. And what happens when you get apps that look pretty much the same all the time? Well, sorry, I messed up the order, but yeah, what if I told you you can just sort of auto-generate the app? And that's my friend Alex Wilmer right here when he came up with the idea of let's make something that just auto-generate this thing. And so let's kind of go back one slide because I messed up the order. Of basically the whole oral anatomy of the system that we work with. So So we get a bunch of files from different data sources. That's a bunch of database right there. We normalize all of this data, so this data can have like a lot of relationships in them. Can be a bunch of files, and then files might have different participants related to the file. We extract that data, run what we call the ETL, or extract, transform, and load, where we essentially just denormalize all the data and index it into Elasticsearch and build an API on top of that, expose it through the web, and make the UI to let people search through it. And Elasticsearch, for those of you who might not be familiar, is basically a document store that's optimized for searching, for retrieval. This, by the way, actually I found it from, half of this diagram was actually found from one of our architecture diagrams. We already saw that. So the magic sauce was basically, Elasticsearch has this thing called the mapping, which is essentially kind of like the schema of a database. Well, you know what also has a schema? GraphQL. So we'll take, the magic sauce is basically we'll just take Elasticsearch mapping and turn it into GraphQL schema. And so we ended up with a product that looks something like this. Still very much a work in progress, but let's see if I can show a quick demo of the thing in action. By the way, so this is, actually before we go into that, this is the actual product, ultimate end product that of a portal that we just finished building like end of this week. So as you can see, it's basically a faceted search page. We have a table of all a bunch of genomic files. These files are huge, 20 gigabytes. A total of this portal currently we have 750 terabytes of data and growing. This is not the biggest portal. 28,000 files. We do have like other portals that we built with like 200 and something thousand files in them. So that portal, while it takes a lot of work to go from this to that, this is basically what's driving the search site that we just saw. So wait, one sec. I'm going to take a look at Elasticsearch. So Elasticsearch, like I mentioned, is a document store that is optimized for searching. So here I have actually already created an index of a bunch of artists. I just created an index of artists in Elasticsearch. And let's take a look at the mapping. Enter. So this artist index only has a couple fields. We have the artist index, only one type of documents we're going to store in this called doc, not very creative. And then each artist is going to have different albums of type, of nested type, that the nested because that's essentially another entity. And then the albums would have some names of the type keyword. And albums have songs, which are again nested because that's another entity that was supposedly ETL and like harmonized or what's the word, normalized? I can't remember which, into this data format. Right. So you got the mapping. The actual, sorry, it's a bit hard to do this with one hand, so I'm going to put this down. All right, the actual index basically looks like this. So we have a list of all the artists. This one's named Bruno Mars, and he has a bunch of albums. I'm not very creative with my naming, obviously. But so now we have a mapping, an index with a mapping, and we're going to go into a ranger, which is the product that Alex has helped build. Well, I already did this, but sorry, I kind of don't want to go through it again. So I can create a new one actually, called artist. So through a ranger, we can create versions of the API. And so we're going to create, I should have called that V1 or something, but on V1 we're going to have an artist type that's pointing to type artists, and the type that we store in there is doc. Let's just hit create. So it looks like a ranger was able to pick up the mapping file. Go into artists, and we see that it's got all these fields, so it was able to pick up the fields okay. Through here you can change the different types this type is essentially going to be used at the UI level to change the rendering. Should go back, and then if we hit arrange, just going to quickly refresh this because I might have messed something up earlier today. Yay, now we have an API. So to show you that API, so basically I have a server, the arranger server, listening on port 5050. I named this artist. Oh, spelled it wrong. Yeah, we now have a GraphQL API that's basically spun up for that index. So through this API, you can run all kinds of aggregations. Let's say artists aggregations. And I want all the names of the artists. I'll just try enter. Oh, right, of course. Alex must be laughing at me inside right now. Key. So we want, whoops. Yeah, so we get two artists. We can see that there are two artists in this index, Bruno Mars and Michael Jackson. But what's an API without the UI to come with it? So I'm gonna actually spin this one up because I'm a little more confident about that one working at this moment. Right. So Arranger also actually provides a bunch of UI components that can be composed together to create a portal right now. So this portal looks pretty similar to what I just showed you, right? That's because essentially we just strip out all of these components that are pre-hooked up to the different GraphQL queries and just compose them into a product, an end product. So in a way, we kind of just built a portal right there on the spot. But of course, there's a lot of work that came out and that would come after that in order to actually have a final portal. So recently, we finally released a new product. So we had a little review of all the pros and cons, all the wins and the challenges that we've had with this kind of approach to using GraphQL. Some of the wins first. So this project, away from GraphQL, basically enabled us to share a lot of common logic between different products. We actually built 2 different products in parallel together using the same code base. We can fix bugs in the same common place, and that will be fixed for multiple products. And some of the GraphQL specific wins that we've got, although there are a lot of other wins from this project, but I'm going to focus on what's relevant to GraphQL here. We essentially get a built-in documentation thanks to the schema of the API that we built. So a lot of time when we get like new developers coming in, or other developers from other institutions who wants to use the same API or consume the API that we've built, and I get asked about whether so-and-so data was available, and the easiest thing to do is essentially just point them to the GraphQL schema, and they can inspect that and find it out for themselves. We also get a built-in spec sheet, essentially, of the API. So there are things that were defined in the schema that maybe we haven't had the time to implement yet, but essentially those what's defined in the schema kind of worked as a roadmap for us to know what to implement and how the thing should behave moving forward. We also got a much more approachable API for interacting with Elasticsearch. For those who might have worked with Elasticsearch, you probably know that the query language is very verbose. It's probably one of the most verbose like query thing I've seen out there. And then the combination of GraphQL plus React significantly reduced the amount of state that we had to hold on the client side. So looking at the portal here, really the only state that we're holding is the only global state that we're holding is the filter that gets applied to the entire index. It follows a structure we call the SCONE, short for Simple Query Object Notation. And that essentially drives the entire portal. Every time the SCONE is updated, all the components would just refetch their data to update. So there's not a lot of state we had to manage. So GraphQL, all the things, right? Well, like anything, there are always catches. So one does not simply GraphQL all the things. There are a lot of things that we learn, of course, again, away from GraphQL, but I'm going to focus on what's relevant for GraphQL. One thing we learned was the Godzilla query really got us. By exposing an API that allows the client to ask for crazy amount of data or really complex data, we found at times there were some deeply nested queries somewhere in there that the client can make that can completely hammer the server. So some of this, I think, came back to like we had a pretty ambitious API design, like a pretty ambitious schema, and beautiful APIs always come at a cost. In this case, well, the cost can be complexity, performance, maintainability, whatnot, all kinds of things. But for us, it was performance that got hit real hard. Although this is not really a GraphQL only problem, I think there's a lesson to be learned from what we experienced. We were using Node.js for our GraphQL API, and at some point we realized that, well, actually the day we went live for a demo, beta demo of the product, we found that one of our feature was only able to support like 2 people at once. So it took a lot of investigating, and ultimately we found that there was some query in our schema that was doing a lot of data wrangling to fit the shape that was defined in GraphQL. This might be okay for a lot of other languages, but in Node.js, this really hit because it's single-threaded, and of course you don't want to block the main thread. So avoid heavy compute. And this is, of course, not just in the case of GraphQL. This is true for whatever technology you, even if you're using REST, you have the same problem. But GraphQL essentially allowed us to not realize the problem was there. And then, so we had to take a step back. And initially, we thought it was Elasticsearch that maybe was slow. So we scaled up Elasticsearch, adding more nodes, didn't do anything different. So ultimately, we found that the bottleneck was more likely the API that we were building. And so this relates to another, like a couple other lessons, but so coming back to what we were doing, like the overall architecture of the portal. The point of running the ETL from the original data source to Elasticsearch was to index all of this, and that's where we do all of these data wrangling to come up with the searchable data up front, so that we don't have to do all of that joins and stuff again when the user is asking for this data. Effectively, by having an API that was a little too ambitious, we kind of defeated that purpose. So ultimately, we were able to overcome this challenge by parallelizing the resolver, basically better implementation of the logic. But even then, it was not good enough. And it was ultimately determined to be because we were trying to bring the data model from the Elasticsearch data model to another new data model that we define, all done in Node.js. So we ultimately decided that this feature was better implemented, separated from the data model that we were going through with GraphQL. So essentially, we re-implemented it with REST on a completely new endpoint. But then that that means we lost a bit of a part of me kind of died when I had to do that. Because we lost the binding between this feature and the data structure that we know works. It was always dangerous to re-implement something anyway. So we have like a split logic. So knowing what we know now, what do we have done better? We also have some other lessons that we learned. A couple of fields in our schema turn out to be just typed as JSONs, and it's kind of like TypeScript or any other like type system. Using generics a lot of times defeats the purpose. And so in this case, we did look into how can we type this better. Unfortunately, the data structure for this filter type was very polymorphic. So some fields could be objects, but they can also be arrays of objects of different shape, depending on the values of what you pass in different fields, in a different field. So that was a challenge that we're still trying to find ways to overcome. If any of you guys have experience sort of working with GraphQL in that, like modeling that type of data, please let me know. It'd be great to learn. Another thing we learned was that some of these sort of anemic apps where we completely separate the data from the domain level logic doesn't benefit as much from GraphQL as those where the GraphQL is basically modeling the domain like explicitly. And so the lesson there is that really try to model the domain that you're working with. In our case, we ultimately found that the product that we were building is a Elasticsearch wrapper that provides a nice GraphQL API on top of Elasticsearch. So Elasticsearch was the domain that we're working in. That sort of justifies what we are now trying to achieve, which is updating this API so that it more closely model the data structure that is coming from Elasticsearch. That way we would still get the beautiful API, the beautiful schema, but at the same time like not have this performance issue as well. So ultimately, like anything, it takes work to benefit from GraphQL. And that was it. Thank you.